So we're talking about heat exchangers now. This we'll say is an introduction to heat exchangers. There's like entire classes you can take that cover heat exchangers. We are just taking 2 lectures to talk about it. There's a lot of depth here. This just gives you an idea of how they work and what the energy considerations are as part of this, how you go about analyzing them, but realize that there's kind of a lot more to it than necessarily what we're talking about here. All right, so let's maybe define a heat exchanger. Heat exchanger is a device that's used to continuously transfer heat from one fluid stream to another. So maybe we could argue about whether it's always one fluid to another. There are examples of heat exchangers where basically you're taking a fluid, putting it through, say, a phase change material, and using that to store energy. Right? That's still technically a heat exchanger. It's just that one side is not really moving. Or maybe you have some kind of a particle system or concrete or something you're trying to heat up. Right? These are still basically heat exchangers. They behave as heat exchangers. You can model them that way, but we'll be a little loose with our definition. All right, but that's the basic idea. You have a device that's trying to move heat purposely from one thing to another. So you tend, in these type of applications, to really care about the fact that you're buying this thing. You have to buy a certain amount of material, and then you want to base the performance of that, or somehow relate the performance of this device to how much of it you have to buy. Okay, so some examples. These things are everywhere, but some examples would be go open your refrigerator. Right, there's in the back of your refrigerator, there's typically like a finned-looking thing with some tubes going through it. There's usually a fan blowing over it. That's a heat exchanger. So that is trying to remove heat from the refrigerant, remove heat from the refrigerator into the refrigerant, which then goes to a coil on the back side of the refrigerator, right? So 2 heat exchangers in your refrigerator. Other examples would be furnace or AC, or air conditioner. So again, you're trying to move heat from one place to another. If you were to look in the duct inside your furnace, you would see that there's the combustion area, there's a gas furnace, and then inside the combustion area, that hot gas goes through a heat exchanger. So then you're pushing air through the other side of that. So you're trying not to mix the combustion products with stuff you're breathing. So you have this heat exchanger to kind of separate those 2 flows. Air conditioning is the same way, right? You have a refrigerant that's circulating and you're rejecting heat to air. So another application. Other examples, right? Power, power cycles. By that I mean like a Rankine cycle, like in a electricity production application, radiator in your car, many others, right? Etc. Heat exchangers are everywhere. So an important outcome of this class is like knowing how to work with heat exchangers. Okay, so that's the general idea. It turns out that the fact that a heat exchanger has a certain geometry, like let's say you have a pipe and then outside of that you put another pipe. So let's just kind of look at what I'm drawing here. So let's say your simplest possible heat exchanger is you have a tube or a pipe. You put that inside another tube and you flow 2 fluids right across each other. That's a heat exchanger. You could potentially have heat moving from one to the other. But just that geometry by itself isn't enough to decide whether or not, or how it's going to perform, right? How it's going to behave. It actually depends how you pipe the thing, like how you actually move fluid through it. So there's 2, I guess, most common examples. One is parallel flow. The other is counterflow. And as the name kind of implies, in parallel flow, let's say you have the hot fluid coming in on this side, and that sort of goes on the shell of this. At the same time, you have cold fluid going in the inner pipe in the same direction. So it's really the direction of the flow that's important. We call it flow configuration. In counterflow, the opposite would be true. You have, say, hot coming in and going this way, and then you have cold going the opposite way. All right? As it turns out, that most of the applications you're going to want to use heat exchangers for, you want to do counterflow. And we'll talk about why that is. So let's maybe sketch out what the temperature profiles look like for these types of systems. First, let's do a parallel flow. Give myself a little room. So I'm going to plot temperature on the y-axis as a function of position along the heat exchanger in the x direction. So if we're just drawing coordinates here, right, let's say this is the x direction on this parallel flow. So I'm going to give you a better axis than that. All right, so let's maybe plot the temperature profile. First, the hot stream. So you're coming in on the left. You have, say up here, this would be THN. That's the hot inlet temperature. Also coming in, it's a parallel flow. On the left would be TCN. So down here, TCN. So we know kind of what's going to happen. I guess you're going to have some heat that's going from the hot side go to the cold side. So that hot side's going to lose temperature. The cold side's going to gain temperature. And somehow if you made this thing long enough, I guess what would happen is those two temperatures would eventually converge. Right? So if you made this pipe, 1,000 meters long, and it was a relatively low flow rate, basically it's going to converge to the same temperature. How it does that is kind of interesting. I guess at first, the rate of heat transfer is dictated by the temperature difference, which is big. And as that temperature difference gets smaller and smaller, the rate of heat transfer goes down. So you get this kind of convex, concave type profile. So it's, say, looks like this. So your cold might look like this. Your hot might look like this. And eventually these would converge at some point if it's long enough. If it's a very short pipe, then you would just, you'd be leaving at some intermediate position. Okay, so a couple things. The final temperature difference at this point would be called the approach temperature. So approach temperature. And normally we talk about the approach temperature being the closest temperature on either side. So if it happened that closest was on the left, you'd say that the approach temperature is on the left. It's just the closest that the two fluids get to each other in temperature. All right, let's look at the other configuration here. So this one's a little trickier, right? This is now counterflow. So again, we have temperature and position. So now we have to look at what's happening on the left, what's happening on the right. On the left, we have, how do I draw this? So, okay, I'm going to do something kind of annoying. I'm going to say that x is going the opposite direction here, just because it makes it easier to plot. So let's say at x equals 0, we have hot fluid coming in. Right, so our hot fluid coming in is still at the same temperature up here, this THN. But now at x equals, I don't know, let's call it L, it's the far left end. I have cold fluid going in, right? So that's at the other end. So now my cold fluid going in is say over here. So this is TCN. So now I've got one fluid going this way on the plot, another fluid going this way on the plot. How do they kind of line up? So again, if you made this thing long enough, you make it infinitely long, somewhere in this system, the temperatures will converge. But what will they converge to? Well, if you really think about it, if I made this long enough, I've got this hot inlet temperature here. So if I make this long enough, my cold outlet is actually exiting right where the hot fluid is hottest. So theoretically, I could get the flow to converge to the hot temperature. And likewise, I could get the hot flow to converge to the cold temperature, just sort of depending on how I play with the flow rates. So what that means is these fluid flow streams kind of look like this. So let's say the hot might do something like this. Now where this point over here is TH out, and this is flowing in this direction as I've drawn the arrow. TC in might do something like this. Right. So now this is TC out over here. Okay, so these are it's very different behavior, right? It's very different between these two flow configurations. In this case, as I've drawn it, I guess the approach temperature, let's just circle it over here. Right, this is my approach temperature. Because that's the point where it's closest. Okay? So hopefully this all makes sense. The way I've drawn the lines in this example, they're straight. In reality, again, the rate of heat transfer depends on that temperature difference, so they might be slightly convex, but as I've drawn them straight.